good morning. The topic that we have for today is support machines. It falls in the larger class of algorithms called kernel machines. So why an SVM is interesting? It's primarily interesting from a theoretical perspective, and also of late it became very interesting for the practitioners, primarily because this particular algorithms, the support machine class of algorithms are built over firm theoretical foundations. Here, the problem that we address is posed as an optimization problem, and then you solve the optimization problem to get a solution to the problem that we address. So it has firm theoretical foundation that we are going to see today, and of course, it gives very good generalization performance in many applications. Some of the successful application areas you can read through. It involves internet businesses to financial systems. People have applied support machines in various categories of problems. Yeah, this is not an exhaustive list. This is a list that I've prepared maybe like a few years back. So every other day, a new application area gets added to this very interesting machine learning paradigm, or the application area of this very interesting machine learning paradigm. And another very interesting aspect of this particular class of algorithms is there is a lot of open source material out there, which you can easily access, and I'll give you links to some of those material. So you have easy access to open source material. It has firm theoretical foundation and proven generalization performance in many application areas. Let's start with a recap of what we have earlier. So this is a two-class classification problem. Our agenda is train the machine in such a way that the machine can classify again any given new point to either of these classes, either as a class 1 or class 2. So we have given the Maruti infantile case over here. Formally, this will be the learning paradigm. The problem in hand will be posed as a problem where you are supposed to learn from a training set, from the information available in a training set in the form of labeled, which is in the form of labeled data points, where xi is a representation of an entity, and basically it can be a photograph, it can be a record representing a human being, it can be a record representing a student, it can be a record representing a legal document. It can be an email, it can be anything, and the categories depends on the domain of application. All right, and you have m such training examples, and the supervised learning paradigm that we've already seen, which says like, okay, you just learn from the learning algorithm is trying to learn or mimic the performance of a supervisor. So there is a generator which generates data. X, it can be the photographer or the one who writes the email. The teacher who labels the data is called the supervisor. So the supervisor gives a label to X, let it be Y, and we have m such examples. What the learning algorithm is supposed to do is it needs to index a model. Labeled here as f parameterized by alpha. Given an x, f alpha of x will have an outcome, will produce an output. Right, and when the output matches y, you say like the correct label is obtained. Rather, the learned model is able to perform in such a way that it is able to do correct things. If it's a classification context, you'll say like if y matches that of, or f alpha of x matches that of y, then we'll say the classification is correct. And we've seen measures of performance like confusion matrices and computations around it. So that's the typical model, and problems are, I don't want to spend time here, we had enough of it. All right, so this is a two-class classification context which context is linearly separable. We have got points belonging to two classes over here. We have say class +1 belonging, represented as squares, and class -1 represented as maybe circles, and there is a there is a clear separation between the two classes, points belong to two classes, and which is linearly separable, which means that you can actually, in the two-dimensional space, you can actually learn a line which, or the parameters of the line which separates the two classes, and when a new test point comes in, what you do is you check whether the point is above the line, you select. So let's label the line as, or represent the line as W transpose X plus B equal to 0. That's the equation of a hyperplane, or the equation of a line in the 2D space. W transpose X plus B equal to 0. When a new point is getting into the context, when you have a new test point, you compute W transpose X plus B, and if W transpose X plus B is greater than 1, you say like, okay, the point belongs to the class of squares, otherwise it belongs to the class of circles, right? W transpose X plus B less than 0, you say like it's the class of zeros, and the 0 case can be assigned to any of these classes depending on the context. All right, and we have seen an algorithm which can learn a line in the 2D space or a hyperplane in the n-dimensional space. And what is that algorithm? The algorithm is Perceptron, right? We've seen an algorithm which can learn a hyperplane. And what Perceptron does is, starting with any initial test for W and B, or W0 to Wn, what it does is you incrementally update the weights in such a way that so changing W is equivalent to rotating the line, and then you essentially converge to a point where you see that, okay, every training point for which I have access to, I see that the points are separated now, right? It's doing a correct classification. So essentially a perceptron can learn a hyperplane which separates two classes when there is a linear separability, which is good. Can you go beyond this? And the line or the hyperplane to which the perceptron will converge to will depend on the initialization, and will also depend on the order in which you present the points, right? I can see, or you can also verify that a very perfectly oriented hyperplane or a line is drawn in the problem that is mentioned, that is represented in the screen. You have a hyperplane which is midway, right? And perceptron may not always result in the midway hyperplane. It can actually come out with a hyperplane which may go like this. See, for example, like this, or a hyperplane which goes like this, which just separates, right? Which goes like this, or any orientation can be there for the hyperplane that the perceptron will converge to, because it will depend on, and all it ensures is for the given set of training points, it does a reasonable job, right? That's what perceptron is all about. A linearly separable case, a perceptron can solve the problem, right? Right. Then the natural question that will come to anybody's mind who have looked at perceptron seriously is, yeah, I can draw n number of hyperplanes or lines in the 2D case, which can separate these two points belong to these two classes. Which one is the best, right? And this question was addressed by supported machines. Supported machines is again an algorithm which tries to learn hyperplanes. It may not be in the original data space. We'll come to that context. It can be in a transformed transformed data space. But essentially, it's a problem which can learn. It's actually an algorithm which can learn hyperplanes, which separates points belong. In the simplest case, points belong to two classes, right? So today we are going to look at SVMs which solves two class problems, right? And where there is a linear separability is where we start with, and we'll move on, right, from there to nonlinear cases. So hyperplane learning is a paradigm that we look at in the case of supported machines. And the natural question that the SVM asked is, given a context like this, have points belong to two classes which are linearly separable, there can be infinite number of hyperplanes which will essentially separate the two classes, right? Linearly separate the two classes, right? Which one is the best? And this problem, very specific problem of which is the best hyperplane, was solved by supported machines by posing this problem as an optimization problem. Let's see how it happens. Vladimir Vapnik is a person who came up with the answer to this question. He said the question was, which is the best hyperplane, right? The answer was the maximum margin hyperplane. Don't worry too much about the jargon called maximum margin, or people call it maximal margin hyperplane. One of the ways in which we can look at this problem is, how do we find the best hyperplane? Vapnik said, let's go with the maximum margin hyperplane. How do we find the maximum margin hyperplane, right? That's an actual question. And you can see that the one that goes midway between the points which are on the boundary of these two classes, like I can see like points, these are the boundary points in this class, and some of these are the boundary points in this class. So there are points which are on the boundary of any class. We are considering only a two-class context. So some of these points are belonging to the boundary of this class, and some of these points are belonging to the boundary of this class. All right. Given that context, just do a recap around the notion of a hyperplane. What is hyperplane? Hyperplane is represented in mathematical form as W transpose X is equal to 0, where W0 becomes the P parameter. W transpose X is equal to 0. W transpose X plus B is equal to 0 if you don't want to have a W0 there. So it is defined in terms of the parameter W, right? And what is W? W is a vector orthogonal to the line, right? And changing W is essentially rotating the hyperplane, all right? So my problem in hand is I need to find out, given two sets of points, I need to find out the midway hyperplane. And I've got many options, right? One of the ways in which you can address this problem is, let us draw parallel hyperplanes, right, through the boundary points in each of these classes. So for example, I can just take these 2 points and I say, okay, I will draw a boundary, rather a hyperplane, which will pass through these 2 boundary points only, and or maybe 3, or these. And likewise, in this context, I can draw a hyperplane which passes through these boundary points, right? Or whatever, these 2, I mean, I can even ignore this. I can draw a hyperplane which passes through these 2 boundary points, right? So the problem of finding the maximal margin hyperplane, he posed this problem as finding out the boundaries of the classes to start with. Once you can represent the boundary or the hyperplane that marks the boundary of these classes, I can always find midway. And we know that a hyperplane is represented by W transpose X plus B equal to 0 is actually like the representation of hyperplane. Let us look at 2 hyperplanes which are parallel to the context, right? Let us draw 2 boundary hyperplanes, which are, they call it canonical hyperplanes. Let us draw the hyperplanes W transpose X plus B is equal to plus 1, which is marking the boundary of maybe the square classes. Let us draw a parallel hyperplane, which is W transpose X plus B is equal to minus 1, marking the boundary of points belonging to the circle classes. Now, once I draw these hyperplanes for some W and B, which is essentially the parameters defining the hyperplanes, the parallel hyperplanes, and you must have by now realized that, yeah, it's the same. Basically, like all that changes here is like the location of the hyperplane. These are parallel hyperplanes, which means that we'll have identical W's and B, and one is placed at W transpose X plus B is equal to minus 1. The other boundary is W transpose X plus B is equal to plus 1. And now my separating hyperplane or the decision surface will be the midway W transpose X plus B equal to 0. So putting things back to context, I've got many options. What I can do is I can draw parallel hyperplanes for each of these candidates by passing through some of the marginal points, right? And I can consider the moment I have got these boundaries marked, I can find the midway between these boundaries, and then I'll call that as the candidate, right? One of the hyperplanes that I'm considering to be the midway, right? So back to Wapnick's answer, I need to find out the one that's midway. Let us look at the boundary hyperplanes, and once I have the boundary hyperplanes, I can always look at the midway hyperplane, which is double transpose x plus b equal to 0. The boundary hyperplanes, when the boundary hyperplanes are double transpose x plus b 0 plus 1 and minus 1. And I know how to compute the distance between the boundaries. So I would, like, if I just draw, say, I'm considering only this particular point as a boundary point, right? I can draw a hyperplane like this, double transpose x plus b is equal to minus 1 passing through only this point, like this. I can draw like this. And I can also draw, considering only this point, I can parallelly draw, I can draw a parallel hyperplane which goes through, which is parallel to this hyperplane. I can draw these two lines, W transpose x plus b is equal to minus 1 will pass through this, W transpose x plus b is equal to plus 1 will pass through this. I can scale W and b in such a way that this can happen. And the moment I have it, what will happen is, like, I'll get, this will be my boundary, the separation between these two lines will be only this much, all right? I'll get a line through here, I'll get a line through here, I get this as a margin. So somewhere midway in between, so my W transpose x plus b is equal to 0 will pass through somewhere here, right? Midway between the boundary marked by this point and the boundary marked by this point. Likewise, I can, for each of these candidates, I can get a, what do you call it? I can, instead of drawing this line directly, I can draw parallel hyperplanes passing through some of the boundary points, and these lines will essentially then become the midway lines, right? The lines which are midway between these two. And what is going to happen there is, see, this is this looks like an ideal line, right? I can have a boundary over here. As I said earlier, I can have a boundary over here. I may get a midway like this also, right? And I can see that the marginal separation goes, if I draw lines the way I have explained here, and the marginal separation between these two boundary lines will be lesser compared to the marginal separation between these two boundary lines. All right. So we'll come back to this. This is what Wapnick said. SVM is essentially like, when you're looking for the best hyperplane, SVM can find the maximum margin hyperplane. Vladimir Wapnick, the scientist, said. SVM learning problem, let us formulate this problem as an optimization problem. To be very specific, a quadratic programming problem, material on that I have already shared. A quadratic programming problem is essentially a problem where the objective function, it's a constraint optimization problem, where the objective function to be considered becomes quadratic, and the constraints are linear, all right? And he said the maximal marginal hyperplane, when we actually learn the maximal marginal hyperplane, we can represent this maximal marginal hyperplane as a combination of data points, right? And he called those data points which essentially define the maximal marginal hyperplane as support vectors. So support vectors are the data points defining the maximal marginal separating hyperplane. SVM, back to why SVM, firm theoretical foundation, good generalization performance, and easy access to open source. All right, let us look at formulae. Right. So far, I was only giving you stories. We started here. We said we need to find the best hyperplane. SVM said the Vladimir Wapnick's answer to it is, let us find the maximal margin hyperplane. How do we find the maximal margin hyperplane? Margin he defined as the margin of separation between the boundary hyperplanes or canonical hyperplane. These hyperplanes are called canonical hyperplanes. These are hyperplanes drawn through the boundary points, and you can find the distance between these two hyperplanes. It's called the margin of separation. I want the midway line where the margin of separation is maximum. So I can draw parallel hyperplanes like this, and I also get a margin here, but that margin will be lesser, and I'll also get a midway line there, but the margin of that particular candidate would be lesser compared to this. So the one that is midway would be like the one with the maximal margin, because it respects the boundary. Also make sure that the separation between the boundaries is maximized. So at any case, from a generic context, if you are looking for finding an abstraction which will separate out, which can distinguish between two classes, which can discriminate, you will be looking for an area or a context or a separating mechanism where you have maximal separability, right? Vapnik's answer essentially falls into that category. And how does he actually do it? All right. The first step that SVM does is, this is a two-class context. We have points belonging to square classes and circle classes. The first step in defining SVM is, let us scale W and V in such a way that for any given pair of boundary points, one belong to the one class and the other belong to the other class. In our case, the square class and the circular class. Take out some boundary points out there, draw parallel hyperplanes with parameters W and B. So W transpose X plus B is equal to +1 will mark one boundary, and W transpose X plus B is equal to -1 will mark another boundary. Now, the moment I have got these two hyperplanes defined, I can find the maximum, the margin of separation between the two. So these are two parallel hyperplanes. W transpose X plus B is equal to +1 is one hyperplane marking the boundary of square points. W transpose X plus B is equal to -1 marking the boundary of the circle points. I can find what is the distance between these two parallel hyperplanes. W transpose X plus B is equal to +1 and W transpose X plus B is equal to -1. You can easily see that it's 2 by norm W. So it's nothing but when you see the calculation out there. So it's distance between two parallel hyperplanes. So the margin of separation, the moment you have identified two candidate boundary hyperplanes corresponding to a candidate midway line, all right? W transpose X plus B is equal to +1 and W transpose X plus B is equal to -1. You see that the margin of separation between these two is 2 by norm W. It's evident over here. Once we have this mathematical notion, all right, this is one candidate. I can have n number of candidates for this hyperplane. The boundary point, the boundary hyperplanes or the canonical hyperplanes may be this for this particular line, right? This may be representing parallel to this. There may be a line over here. There may be a boundary over here, all right? And some other point over here may be considering only this boundary point, and probably this point here will draw another. So some of these candidates will have another set of boundary hyperplanes or canonical hyperplanes. So for any of these candidate, right? Just for this candidate, we see that, all right? The margin of separation is 2 by norm W, right? What am I looking at? I'm looking for the best hyperplane. And Vapnik said the best hyperplane is the one with the maximal margin, right? And margin mathematically is defined here as margin of separation between the boundaries. And the margin of separation between the boundaries in this case is mathematically represented as 2 by norm W. This is nothing but the separation between two parallel hyperplanes, 2 by norm W, right? So for any candidate, now I have n number of candidate hyperplanes and the corresponding boundaries. For each of these, W transpose X plus B equal to 0 and the corresponding boundary hyperplanes W transpose X plus B is equal to +1 and -1. I do have 2 by norm W as its margin of separation for that particular hyperplane, all right? Which means that if I say this is W1, this is W2, W3, W4, W5, W6, and W7, the margin of separation between the boundaries corresponding to this particular hyperplane would be 2 by norm W1. Corresponding to this hyperplane be 2 by norm W2. This will be 2 by norm W3, 2 by norm W4, 2 by norm W5, 2 by norm W6, and 2 by norm W7. I've drawn only 7 hyperplanes. I'll have n number of such hyperplanes. Right? So I got 2 by norm W corresponding to like the margin of separation that this particular hyperplane would have, meaning it's essentially the distance between its boundary marking hyperplane, the canonical hyperplanes. Corresponding to this, there will be some parallel hyperplanes and likewise. So I have the notion of a 2 by norm Wi corresponding to any hyperplane, candidate hyperplane, which is a candidate to be considered as a maximal marking hyperplane. What is my agenda? My agenda is to find that hyperplane. Among all these candidate hyperplanes, my agenda is to find that hyperplane. I repeat, I want to find that hyperplane where the margin of separation is maximum, or the maximal margin hyperplane. All right, and I know the margin now is mathematically represented as 2 by norm Wi. All right. So how do I maximize this? How do I maximize this? How do I find the hyperplane with the maximal margin of separation? 2, you can't do anything. The margin is 2 by norm Wi. I'll find that hyperplane I such that 2 by norm Wi is maximized. Right? How do I maximize 2 by norm W? The only way in which I can maximize 2 by norm W would be to minimize norm Wi. Right? 2 by norm Wi can be maximized. I want to maximize the margin of separation. Among all the candidate hyperplanes I have in hand, I need to find that hyperplane with maximal value for 2 by norm Wi. Right? I have an optimization problem which says maximize, right, 2 by norm W. At the same time, this is a linearly separable context which says that this, when I consider Wi, the hyperplane represented by Wi dot x is equal to 0, or Wi dot x plus Bi is equal to 0, should be able to separate the points perfectly, right? It should be it's a linearly separable context, and the hyperplane should be able to separate the classes into 2 with that line, and only those lines or hyperplanes will be considered. So I have an optimization problem here, right? I can pose the problem of selecting the maximal margin hyperplane now as, I know, like, for each of these Wi's, the margin of separation is 2 by norm W. I'll say my problem reduces to find that hyperplane which maximizes 2 by norm W, at the same time classifies points belonging to let's call this +1 classes, the square classes +1, and points belonging to circle classes as -1. Let's use that label for convenience. My problem reduces to find among all these potential hyperplanes or candidate hyperplanes, let us choose that hyperplane with maximal margin or maximal value for 2 by norm W. At the same time, points belonging to the plus classes and also the points belonging to minus classes are perfectly classified. Right? So I have an optimization problem. I have reduced the problem of finding the maximal margin hyperplane, which is essentially what SVM does, to an optimization problem which says choose that hyperplane, right, which maximizes 2 by norm W, which is the margin of separation, and achieving correct classification. Right? Points belonging to square or plus should be on this side of the hyperplane, whatever be the hyperplane that I choose. Points belonging to +1, if I take any test point over here, Wi transpose that test point should be greater than 0 here and should be less than 0 over here. If I consider like the boundaries, I say, like, I can say, yeah, I mean, I don't want anybody in the boundary, I can even push further. But all I want to say is my problem of finding the maximal margin hyperplane now reduces with all the canonical hyperplanes or what are the boundary representation schemes being considered, reduces to find that hyperplane which maximizes 2 by norm W and achieves correct classification. Or rather, if I represent the points belonging to these classes as +1 and points belonging to these classes as -1, my hyperplane is Wi. It's basically the candidate under consideration. Wi and the point is x dash. Wi dot x dash. Alright? That will be like kind of the value that I compute, and that should be +1 here, or plus it should be a positive value over here. It'll be 0 or I would say it should be more than 0 over here. And any point x dash which belongs to here, wi dot x dash should be less than 0. Right? So the problem, let me formally represent, the problem reduces to, among the candidate hyperplanes, find out that hyperplane which maximizes 2 by norm w and achieves correct classification, which means that with that particular hyperplane, if I compute w transpose x should be greater than 0 for the points belonging to the square classes and should be less than 0 for points belonging to the circle classes. If we represent this as +1 and this class is -1, I can very well say like the label of the points belonging to the square or the circle, right? Here in this +1, this is -1. So W transpose X for any point here, for that particular hyperplane or any hyperplane for that matter, because it's a linear separable case, W transpose X will be positive into +1 will be positive, all right? And for any point here, W transpose X will be negative, and the label of this particular points belong to this particular class, we represent that as -1. So yi, the label into W transpose X for points belonging to here will be also positive, because the value you compute for the any point over here, W transpose X, will be negative over here, negative into -1, some negative number into -1. Minus into minus will be positive. So I would say my problem reduces to maximize 2 by norm W such that correct classification. I'll explain correct classification. Correct classification occurs when the label of the test point under consideration into W transpose X, or if you don't want to absorb B into W0, the label into W transpose X plus B should always be positive, right? That is the case because any point over here, W transpose X plus B or W transpose X will be positive, and the label for the points over here, we have represented that as +1. So the label +1 into W transpose X plus B is positive over here, and the points here is labeled as -1. So for any point over here, W transpose X plus B will be -1 because we are assuming linear separability, and so W transpose X plus B into, that will be negative, into -1 will be again positive. So the problem reduces, the maximal margin hyperplane learning problem reduces to maximize 2 by norm W, because we are looking for the maximal margin hyperplane where 2 by norm W is the margin of separation for any candidate. Maximize 2 by norm W such that correct classification. Correct classification can be explained as the label of the test point into W transpose X plus B computed for that test point should be positive. So the problem reduces to maximize 2 by norm W such that yi, the label corresponding to the test point, into W transpose Xi plus B is greater than or equal to 0, positive, right? Let's get into the mathematical representation. All right. So we'll start with the linear hard margin SVM. Right. This is the, and I'm going to look at each of the contexts that I explained to you in a more formal manner. Be very attentive because it has involved math. Let us assume that linear hard margin SVM assumption is, we assume that no point falls off the boundary. Everybody is well behaved. If it's a square, it will be always on this side. If it is a circle, it will be always on this side, which is not a realistic assumption. To make our life simple, we'll start with a linear hard margin. Hard meaning we don't permit anybody to cross the border. That's what it is. Let us start with defining the hyperplane. It's simple, and you can see that this is W transpose X plus B. So this is just for convenience. We use angle brackets to represent the dot product. We'll start with representing the separating hyperplane as W transpose X plus B is equal to 0. This is something that you've seen even at the Perceptron context. Then we define the functional margin of an example given a point xi yi. The functional margin of that point, or the margin of, essentially it's a margin of it's essentially a notion of separation more notion of distance or nearness, for that matter. So for that, it's essentially represents such a notion, the functional margin. Functional margin, for example, xi yi with respect to the given hyperplane. So we are considering hyperplane called W transpose x plus b is equal to 0. The functional margin of example xi yi with respect to the hyperplane W transpose x plus b is equal to 0 is defined as gamma I is equal to yi into W transpose x plus b equal to yi is equal to gamma I is equal to yi into W transpose x plus b. That's a definition of functional margin. That's a definition. All right. So this is something that I've already told you. All right. If we are marking the points belonging to the square classes as +1 and this classes as -1, you can very well see that yi is either +1 or -1. Points belonging to the square classes W transpose x plus b will be positive. Positive into +1 will be positive. Points belong to the circle classes W transpose x plus b is negative because it's the lower part of the hyperplane, lower side of the hyperplane, and yi there is -1. -1 into a negative number will be positive. So, which means that a functional margin gamma I will be greater than 0 implies that the point is correctly classified. So, given any new test point, if we can compute its functional margin with respect to the given hyperplane W transpose x plus b is equal to 0, and if you see that yi into W transpose x plus b for that point, computer for that point, or rather functional margin, which is essentially I told you like how far you are away, or your notion of we call it similarity, dissimilarity. It's essentially a notion of distance, but you can't call it a distance. I will come there. So essentially, the functional margin evaluated for any given point with respect to W transpose x plus b, if you see that the functional margin is positive, which is an indication that the point is correctly classified, primarily because that's the way we label the points out there. So the functional margin evaluated with respect to the normalized linear hyperplane. So essentially, like you normalize the vector w. W is divided by w by norm w. You get the normalized vector essentially in the direction. And so you normalize b also correspondingly. And if you have that normalized vector, so the normalized, the functional margin computed with the normalized linear function, so w by norm w into x dot x plus b by norm w, you will essentially find is equal to 0. That's essentially like the normalized representation of that hyperplane. And if you evaluate the functional margin with respect to the normalized hyperplane, that is essentially the geometric distance. It'll be called the geometric margin of the point. It'll be the distance. So you can, if you understand vector ladle of vector theory, you can see that w by norm w is nothing but the direction, right? W by norm w dot x is essentially a projection of x onto w by norm w. So how much x is towards w by norm w? So which is essentially a notion of distance. So geometric margin is essentially the Euclidean distance of the point xi by I from the hyperplane W transpose x plus b is equal to 0, f w bx. That's what it is, right? F w bx is nothing but W transpose x plus b is equal to 0. So the geometric margin is nothing but the functional margin. That's the reason why I said I have not properly labeled that as the distance. So the geometric margin is essentially the Euclidean distance of any. So geometric margin essentially represents the distance of a point from a hyperplane. That's what it is, right? So if you don't normalize, what you get is represented as the functional margin. So that's what it is. So these are jargons out there. Task. What is Wapnick trying to do? Wapnick is trying to find the maximal margin hyperplane. How do you find the maximal margin hyperplane? To compare the different candidate hyperplanes. I've got n number of candidates over here. Which one I'll consider, right? This is something that the story I've already told you multiple times. All right. I want to find the maximal margin hyperplane. To compare, right? Among all these hyperplanes, which one is the maximal margin hyperplane? To compare the different candidate hyperplanes, we can rescale w and b. Basically, w and b can be scaled, and you see that from your basic vector algebra, you should be able to say that a 1x is equal to 1x1 is equal to 1x2 or x minus y or x is equal to y is equal to, the line is the same as 2x is equal to 2y, right? Is equal to 3x is equal to 3y. So these are actually representing the same hyperplane, right? 2x1 is equal to 2x2, and you scale it further and you get the same line. It's equal to x1 is equal to x2, and b is essentially what you call an intercept, meaning w transpose x plus b and w transpose x plus b is equal to plus 1, and w transpose x plus b is equal to minus 1 are parallel hyperplanes. So the orientation of the line doesn't change, only the position of the line changes. Right. So to compare different candidate hyperplanes, what we do is we rescale. We actually scale w and b in such a way that the points parameters, so that the points from both the sides of the classes that are closest to the boundary to the candidate hyperplane are at a functional margin of 1, which is essentially like drawing the boundaries. So for each of these points, I can draw the corresponding boundaries, right? Like this, for each of these points, this is drawn only for the midway line. For each of these points, I can draw parallel hyperplanes, which are at w. For this thing, it will be like w1 transpose x plus b is equal to plus 1 and minus 1. So likewise, for this, I'll get canonical or parallel hyperplanes w2 transpose x plus b is equal to plus 1 or minus 1. And likewise, I can draw for every other line. Right? That's what it is. So essentially, like, and we will draw in such a way that so you can find the functional margin. Functional margin, you see that it's not geometric distance. It's essentially like the, what do you call, the geometric distance of, essentially like the Euclidean distance is essentially the one for the normalized representation of w. So so which means that you can scale w and b in such a way that you can draw the boundary hyperplanes for any candidate hyperplane. So to compare the different hyperplane candidates, what we do is to compare these different candidates. What we do is you read to the second item there. To compare the different candidate hyperplanes, you can rescale w and b parameters so that from both sides of the classes that are closest to the boundary to the candidate hyperplane are at a functional margin of plus 1 given by y into w transpose x plus b is equal to 1, which is what I just explained. You draw lines by scaling w and b in such a way that you get parallel hyperplanes. Examples belong to the class plus 1 and minus 1, realizing a functional margin of 1 to the candidate hyperplane w transpose x plus b is equal to 0, or if wb is equal to 0, fall the parallel hyperplanes called canonical hyperplanes. So these are, so essentially like step 2 and 3, what it says is you draw the parallel hyperplanes for each of the candidates. W transpose x plus b at plus 1 and w transpose x plus b is equal to minus 1 will mark the boundaries for the two classes. For each of these candidates, you can draw the parallel hyperplanes, right? At w transpose x plus b, so w1 transpose x plus b1 is equal to plus 1 will be for 1, and likewise for the other class w1 x plus b 1 is equal to minus 1 for the other class, boundary of the other class. For the next hyperplane will be w2 x plus b2 is equal to plus 1 will be one boundary, and for the next for the other class, the class belong the points belong to the other class, w2 plus x plus b2 is equal to minus 1. So for each of these things, you draw parallel hyperplanes at plus 1 and minus 1. Right? And basically, kind of, it's essentially w transpose x plus b is equal to at plus 1 and minus 1. Right? That's what you do. Right? This is what I've said. So and why do we do this? You can actually now you can find how much of a margin I do have as a candidate. Right? When I draw my boundaries, right? Boundaries with respect to points belonging to the two classes. Mathematically, I'm drawing hyperplanes, canonical hyperplanes at a functional margin of 1. That's what it is. For positive examples, yi is equal to plus 1 is something that I've already explained in the earlier case. Y is equal to plus 1, w transpose x plus b is equal to, is always, I'll make sure that I'm drawing boundaries, I'm drawing lines through boundaries, which means that boundaries at w transpose x plus b is equal to plus 1 and w transpose x plus b is equal to minus 1, which means that any point on this class will have w transpose x plus b is greater than or equal to 1, and any point in this class will have w transpose x plus b less than or equal to minus 1. All right, that's how I draw the line, because we are drawing lines at the functional margin of 1. So this is what is explained here. Yi is for the plus 1 points, w transpose x plus b is always greater than plus 1, because the boundary, that's how the boundary is marked. And for the other class, the negative class, where we label the points as -1, and this is the labeling is done for convenience. W transpose x plus b is less than, is always less than or equal to -1. Primarily because the margins are the canonical hyperplanes are drawn at a functional margin of W transpose y and W transpose x plus b is equal to 1. Right. So both cases can be summarized now. For every point belonging to the square, you will get this. For circle, you get this, which means that yi into W transpose x plus b is always positive, is greater than or equal to 1 for all I. The moment you have it, now you can see that once you draw the boundary hyperplanes corresponding to any canonical hyperplane, we know like the boundary, the marginal separation between the boundaries, right? The canonical hyperplanes is 2 by non W. This is something that we have seen over here. Distance between parallel hyperplanes, W transpose x plus b is equal to +1 and W transpose x plus b is equal to -1. The distance between those two hyperplanes is 2 by non W, right? Distance between two parallel hyperplanes, right? It's 2 by non W, right? It can be seen that the geometric separation between the canonical hyperplanes, the boundary hyperplanes, is 2 by non W, right? Since the geometric margin of examples that fall on the canonical hyperplanes is 1 by non W, because this is so for any point which is falling in the canonical hyperplanes, what will happen is any point which is falling in this hyperplane, a boundary point, its geometric distance from W transpose x plus b, this is at +1. So it's basically the geometric distance will be 1 by non W. So 1 by non W here, 1 by non W here. That's how it becomes 2 by non W. Right? That's just what do you call it? Just for the understanding. Right? So the marginal separation is 2 by non W. The marginal separation achieved by the candidate hyperplane W transpose x plus b is equal to 0, or FWB is equal to 0 is defined as the geometric separation with the canonical hyperplanes correspond to the hyperplane W transpose x plus b is equal to 0. So the definition of the marginal separation between separation corresponding to the hyperplane W transpose x plus b is nothing but the geometric separation between the canonical hyperplanes. That's what it is. It is nothing but it is obtained to be 2 by non W. Among the candidate hyperplanes, the maximal margin hyperplane is what Vladimir Vakin suggested. The maximal margin hyperplane is the one that achieves correct classification. You need to make sure that yi in the W transpose x plus b is greater than or equal to 1 for any point, right? Because yi is negative on the lower side and positive on the other side. So yi into W transpose x plus b will be always greater than or equal to 1, primarily because we don't allow anybody to fall between these two canonical hyperplanes, because the boundaries are drawn at a distance of the boundaries are marked by the hyperplane W transpose x plus b is equal to +1 and W transpose x plus b is equal to -1 over here. So among the candidate hyperplane, our problem reduces to finding the candidate hyperplane with maximal margin for 2 by non W, maximal value for 2 by non W, essentially the maximum margin hyperplane, such that the correct classification is achieved. So the last statement there, among the candidate hyperplanes, the maximal margin hyperplane is the one that achieves correct classification and accomplishes the maximal margin or maximum margin separation. Maximize the value for 2 by non W. This can be represented. Can be represented an optimization problem, because now we have two cases, two contexts to be considered. The context is I want to maximize 2 by non W, but at the same time, I want to make sure that I do achieve correct classification. What is correct classification? yi into W transpose x plus b correspond to the hyperplane W transpose x plus b is greater than or equal to 1. Let's write the optimization problem. All right. So my problem reduces to maximize W transpose 2 by non W. All right. Maximize all the parameters. Yeah, I'm considering W and B separately. My problem is maximize 2 by non W such that yi into W transpose x plus b is greater than or equal to 1 for every point, which is correct classification, which represents correct classification. Instead of writing it as a maximization problem, for convenience, SVM represented that as a minimization problem. 2 by non W needs to be maximized. How do I maximize 2 by non W? I can maximize 2 by non W only by minimizing W. Alright? So the problem can be written as minimize over WB non W such that yi into w such that yi into w transpose x plus b is greater than or equal to 1. Correct classification for all I. All right. For mathematical convenience, we have actually normalizing. Say, for example, maximizing x or maximizing x square doesn't make any difference. Right? If you want to maximize x, you can very well maximize x square also. And just for convenience, the problem of maximizing norm w is represented as a maximization of a quadratic function over w, over norm w, and it's written as so not maximization, minimization. So you want to maximize 2 by norm w. The minimization of norm w is for mathematical convenience represented as a quadratic optimization problem, and that's what you see over here. It's written as minimize. So essentially, 2 by norm w maximization is equal to minimization of norm w. This is conveniently represented as minimization as the minimization problem. Minimize over wb half. Again, the parameter is introduced just for mathematical convenience, half of norm w square, such that the correct classification is achieved. yi into w transpose x plus b is greater than or equal to 1 because it's correct classification. That's a representation. So every point has to be at the functional margin of 1 or more. All right, because you don't allow anybody in between. And this is the classic quadratic problem. So let's do a recap. What is SVM? SVM is a hyperplane learning algorithm. What sort of hyperplane it learns? It learns the maximal marginal hyperplane. And I've got many candidate hyperplanes over here. And which one to choose is a question that SVM asked. It said, it'll find the maximal marginal hyperplane. How do I find the maximal marginal hyperplane? Let me introduce the notion of margin. Margin is, for any candidate hyperplane, we can draw parallel hyperplanes, which essentially marks the boundaries of the points belonging to the two classes. Right, and the boundary hyperplanes are represented corresponding to the hyperplane, the candidate hyperplane w transpose x plus b is equal to 0. The boundary hyperplanes are represented as w transpose x plus b is equal to plus 1 and minus 1. All right, and by appropriately scaling w, you can draw such boundaries for every other candidate. Once you have that, the marginal separation will become 2 by norm w. That can be mathematically seen. It's nothing but the for any candidate, the maximum, the marginal separation between the boundaries would be 2 by norm w, right? So my problem reduces to maximizing 2 by norm w, which can be represented as minimizing norm w. All right. At the same time, this is a linearly separable case. Everybody has to be correctly classified, which means that the functional marking yi into w transpose x plus b has to be greater than or equal to 1 because we don't allow any points to fall here. Every point has to be either off, basically like from off. I mean, has to be either on the boundary or above the boundary. And in this case, this has to be either here or below the boundary. So y into w transpose x plus b, the functional marking has to be greater than or equal to 1 for every point for correct classification. And I'm looking for that particular candidate among all these candidates where 2 by norm w is maximized, which means that I want my problem reduces to minimize norm w such that yi into w transpose x plus b is greater than or equal to 1, right? And this problem is called the primary problem for SVM supported machine. So the problem of finding the best hyperplane or the maximal marginal hyperplane is represented mathematically in the case of supported machines as a convenient problem, which is represented as a minimization problem. In terms, as I would say, to be very precise, as a quadratic programming problem, minimize over WB half of norm W square, such that correct classification is achieved via into w transpose x plus b is greater than or equal to 1 for all I. And this is the classical quadratic programming problem, which defines supported machines. And here you can see that the constraints are defined in terms of the number of points. I is nothing but the set of points under consideration. And the way SVM, the original classic SVM, solved this problem is by not by directly solving this problem. This problem, there are many research attempts and there are many publications around solving this problem directly. But SVM had a larger agenda. The larger agenda is currently we are considering only a hard margin case where the points belonging to the two classes can be linearly separated. And this is not a realistic assumption. SVM wanted to go beyond this point. So to make it in a form which is amenable to be mathematically amenable to do such learning, hyperplane learning context possible in transform spaces, SVM has solved this problem by formulating an appropriate Lagrangian dual, and the dual form is called Wolffian. Right? How do you get to, like, instead of solving this problem, the way SVM has attempted this is by representing that as in a dual form called the Wolffian dual. And I've given you the theory around Lagrangian duality. I've given some reading material of, I think, 3 pages long. And how do we get in? We are going to see that. How do we define that Lagrangian dual form? So what is essentially like, and it uses specific conditions called Karish-Kundaker conditions. These are essentially Karish-Kundaker conditions. These are essentially necessary conditions for an optimal solution in the case of a quadratic program. Right? Karish-Kundaker conditions these are the names of the people who propose this condition. These are the necessary conditions, and when the problem becomes convex, and in our case we have a convex quadratic problem. Like you can very well see that. So it's essentially a quadratic optimization. Basically, the objective function is quadratic and it's convex, and the constraints are linear constraints. So you have a convex optimization problem with quadratic constraints. Convex optimization problem with quadratic constraints. Your problem reduces to your context reduces to the Kundaker condition, the KKT conditions. The KKT conditions becoming the necessary and sufficient conditions. So the way you attempt this problem, is by making sure that you leverage the notion of Karish-Kundaker conditions, and then because your context reduces to a quadratic QP problem context with convexity ensured. So your problem is essentially a convex quadratic programming problem, and then you solve this problem by appropriately representing that in a Lagrangian dual form called Wolffian dual. And in the case of convex quadratic problems, KKT conditions are essentially the necessary and sufficient conditions for the solution. All right. So from the KKT conditions, we can see this. Let's move on to looking at how do you actually represent the primary problem in hand as a quadratic programming problem. All right. I'll share a few images which I've already uploaded to your context. Let's look at it. It's already there in your classroom. Just look at this particular thing. So what I've done is, let's go back to our original slide. This is essentially so the way the SVM problem is solved over here is the linear margin, the hard margin problem, assumes problem is solved here is I've told you this is a convex quadratic problem, mathematical problem where the objective function is quadratic and the constraints are linear. You essentially use Lagrangian duality, and the way you derive this Lagrangian dual is what I have represented for you. Let's see that. essentially, right. It's like this. I'll initially write the Lagrangian. I'll write the Lagrangian for corresponding that primal problem. The Lagrangian will be like, all I do is I'll introduce the notion of Lagrangian multipliers over here, and I'll represent. It's essentially a mechanism. And if you read a little about Lagrangian, you must have. Is there in your mathematics for machine learning? What you do is you essentially represent a constraint problem as an unconstrained form. So what you do is the Lagrangian of corresponding that the primal problem can be written as half of W transpose W. It's essentially non-W square is nothing but non-W square is W transpose W, right? Plus, so this is essentially your constraints, and you have m such points. Let's assume that there are m such points. Summation over I is equal to 1 to m alpha I Lagrangian multipliers into yi minus same thing. So if you have read the material, you must have seen that a problem of the form, what do you call it, minimize quadratic function with respect to constraints say ax less than or equal to b, the corresponding Lagrangian can be written like this. Let me see whether I have that material with you, with me, basic notes. So this is basically like, this is the problem of this kind is what you have in place. Minimize a quadratic function subject to constraints of this type, ax less than or equal to b, and say minus x less than or equal to 0. So how do you write the Lagrangian corresponding to this? Lagrangian will be written like this. Lagrangian will be this plus, so essentially representing in a unconstrained form. So 6, this particular thing, plus this is where the Lagrangian multipliers gets in. You have only one, so we have for all I. That's why the summation comes in our case. These are the Lagrangian multipliers corresponding to, so this ax less than or equal to b can be written as ax minus b less than or equal to 0, and 0 less than x can be written as minus x less than 0. So you multiply with the Lagrangian multiplier of z and minus z of x. So basically, like, this is the way you write the Lagrangian. So what you do is you represent your constraint problem in the Lagrangian form, and once you have the Lagrangian form, I've told you this is essentially like it's a quadratic problem with convexity, meaning it's a convex quadratic problem. So the KKT conditions, which are essentially the primal, basically the necessary and sufficient conditions for optima, are called the KKT conditions, and from the Lagrangian we can derive the conditions which are necessary and sufficient for optima, which is the KKT conditions. We'll look at the KKT conditions, and in our case, I've already given you this material. The KKT conditions this has multiple parts. This has primal duality conditions, essentially saying like that's what I said, x minus less than or equal to b. This is primal feasibility. This is the region of this is a feasibility. The regions where what you call the feasible solution would lie. That's essentially the constraints. So is the case with the dual feasibility. The Lagrangian multipliers has to be greater than 0 in the dual feasibility context. And there are conditions called complementary slackness conditions in KKT. And there are stationary conditions out there. So essentially, with respect to the Lagrangian, what you do is you represent the necessary and sufficient conditions. So the necessary and sufficient condition for optima, and the necessary and sufficient condition for optima is defined for this particular case, convex quadratic problems as KKT. You can read the paper on Karish conditions, and what it says is the condition for optima would be these are actually the optimality conditions. You find these are essentially the first order conditions. You say like dou by you compute dou by w the dou by w is equal to 0, which will compute over here will give you. You can compute dou by w is equal to 0. It's essentially like a minimization in this particular context, first order conditions. And what you do here is what you get here is, so by dou by w, the first condition KKT, you get so you get w over here, and summation over alpha that summation will be, and yi into that w dou by w. This will go off, and you get alpha into yi into xi. That's what it is equal to minus w minus summation alpha I yi xi is equal to 0, which means that w is equal to alpha I yi xi, right? And that's the first the other parameter is b, dou L by dou b is equal to 0. That's a first order condition again, which will give you dou L by dou b is equal to 0. That's a part of the KKT, which will give you dou L by dou b is equal to 0. Will give you summation over alpha yi is equal to 0. So this will be the condition. Summation over alpha I is equal to 1 to m of yi. So that is missing here. I is equal to 1 to m. You can write down. I is equal to 1 to m, yi xi will be 0. And the next part of the KKT condition is essentially the complementary slackness. Complementary slackness conditions. If you look at here, the complementary slackness condition is essentially like the what do you call the product of the Lagrangian multiplier into that the x. This condition is basically like y. That's what the y transpose x minus b is equal to. So this is called the complementary slackness conditions. So the complementary slackness condition in our case will be on margin will be alpha I. That's our the Lagrangian multipliers into 1 minus. So our problem was yi into double transpose x plus b is greater than is equal to 1. So in the less than or equal to form, it will be 1 minus y into double transpose x plus b less than or equal to 0. So essentially, like alpha into y, this would be equal to 0 for all I. This is called this will be the. So which means that, which essentially the complementary slackness conditions essentially means that, So this product will be 0 for all I is what it says. What is the meaning of it? It essentially says that there are contexts where alphas can become 0, or there can be contexts where this can become 0. Whatever be the case, the contribution would be essentially like kind of would be I mean will add up to 0. That's what it is. Summation over. So it's a product, right? Product is 0 for all I, which means that there will be contexts where this will become 0 or this will become 0. Right, and the last condition would be the duality condition, which says the Lagrangian multipliers has to be 0 for. It has to be greater than or 0 for all. So these are actually like the research of Karush and Kundakar, which has proven KKT has proven to be the necessary and sufficient condition for a convex quadratic problem. All right. So we just apply the Karush Kundakar case KKT context into our problem. And what you get is, I'll show you the other next part of the problem. I know like this is a little mathematically intensive. The observation is, so if you have this as a piece of paper, right? I would urge you to take this piece of paper and write all these things. I'll give you a minute to write down all this and write I is equal to 1 to m here, so which is missing. Somehow I missed it. Just write down and let me know like if you've done. If you want to, I mean, I know like this is a little math intensive, but you should have at least this level of mathematics to get a feel of the subject, this particular. And that's the reason why people make tutorials called support vector machines without TS. Right? Just write down this part in a piece of paper. All I do is like I've represented the primal problem, the primal convex quadratic problem represented in SVM in a Lagrangian form and apply the KKT conditions. And we need to make some observations from here. And you apply, push it back to the original problem, you get dual. So what you do here is, in the case of primal to dual conversion, Lagrangian duality here, which is called, which is contribution by Wolfey, the Wolfey dual form. What it does is like you apply the KKT conditions back to the primal problem, and you can eliminate the primal variables W and B, and you can define your problem in terms of the dual variables called Lagrangian variables. That's essentially the context. Let me know once you have written all this in a piece of paper. All you do is we just write the Lagrangian, apply the necessary and sufficient condition for optimum. We just compute the necessary and sufficient condition for optima, which is called the KKT conditions for a convex quadratic problem. And the problem is a convex quadratic problem. It's a quadratic function which is convex in nature, and quadratic function becomes convex when what do you call it, you have positive semi-definiteness for that particular function. And you will not see this derivation in most of the tutorials. That's the reason why I thought I'll just write it down, because I do this kind of derivations every other day, because this is what I've been working on for last several years, and those who are interested, we can push it to the limits, but those who are interested only in the current context, I think this should be enough. Understand that SVM problem is posed as a quadratic problem, and the way you solve this problem is you don't directly solve typically. In the classical case, you don't solve this directly, rather you solve its dual equivalent. And how do you get to the dual? By applying the necessary and sufficient conditions for duality, by writing the Lagrangian and applying the necessary and sufficient condition, which is called KK condition, right? That's what is seen over here. I hope you have written, copied. Just a confirmation will do. Have you copied the content? Okay. Okay, that's good. So let's make some observations from this particular context. The observations are here. So let's look at the complementary slackness conditions. We have got equations for W, and we have alpha xi by I is equal to 0 from dou L by dou P is equal to 0, which is primarily like the first order condition over Lagrangian, which is a part of the KKT. And then from the complementary slackness condition, alpha, I told you alpha into 1 minus y into W transpose x plus b is equal to 0. So once you solve, right, see, you have primal variables which are W and B, and the real variables are essentially the ones that are introduced through the Lagrangian multipliers in the case of Lagrangian. Right? Once you solve the problem, you get an alpha for every point. That's what it is. That's what it looks. That's what it will look like when you actually solve the problem. So for every point, what SVM finds is it will actually give you a value for every alpha I. Is essentially like you can think of that as a weight or whatever. Right? It's essentially like how much participation I do have in terms of the solution. In the solution is what alpha I would be like. I mean, if you want a proper semantic understanding, you can. So by solving SVM, what you get is you get an alpha I value. All right, and alpha I is essentially like it's a Lagrangian multiplier. You can treat that as a notion of a participation of a point in the context of the solution, right? So let's look at the complementary slackness condition. Alpha I, this will be 0 for all I. Let's assume that alpha is 0. So if for a particular point, you got alpha I as non-zero. Let's start with non-zero. If alpha is non-zero, which means that from the complementary slackness conditions, the product has to be 0, which means that 1 minus ya into W transpose x plus b is equal to 0. Alpha is equal to 0, right? In that case, 1 minus ya into W transpose x plus b is equal to 0, which means that ya into W transpose x plus b is equal to 1, right? 1 is equal to ya into W transpose x plus b, right? If product has to be 0, which means that alpha is non-zero. If alpha is non-zero for a point, which means that 1 is equal to ya into W transpose x plus b. What is the meaning of this? Ya is the label, W and B are your hyperplane, xi is a point under consideration. The point xi, right, is actually lying on the boundary. So for xi, W transpose xi plus b into ya is equal to 1, meaning this is a point which is on the hyperplane, right? So these points, if you look at these points, so how do you, let's go back and look at this particular equation, just for your understanding. So what is W? W is essentially the hyperplane, right, that you're learning. W is alpha I will have some value. yi will have some value, xi will have some value. This will be non-zero only when all these three are non-zeros. You agree? Now I have a context where alpha is non-zero, which means that I know that xi is non-zero, yi is non-zero. Xi is the data, yi is the label, and alpha is non-zero. So all those points for which alpha is non-zero will define W, right? So W, what is W? W is the definition of hyperplane. W is the definition of hyperplane. The hyperplane is defined in terms of alpha I, in terms of alpha is, yi is, and xi is. We know like these are training points, and alpha I is a solution that we get from the support definition by solving the support definition. For when there is an alpha which is non-zero, which essentially says that this is a point which will participate in defining the hyperplane, and the points with non-zero alpha I values are called support vectors. All right. So where do support vectors lie? When alpha is non-zero, from the complementary slackness conditions, we can see that yi is equal to W transpose x plus b is equal to 1, which means that this point will fall on the canonical hyperplane. All right. Then what will be the hyperplane? The hyperplane is, we represent f wb parameter by wb is equal to w f. Basically with an input x. So it will be W transpose x plus b is equal to 0. What is W transpose x plus b is equal to 0? You know, like this is W, right? You just substitute W transpose x. W is alpha I yi xi x dot x, right? And summation I is equal to 1 to m alpha I yi xi dot x plus b is equal to 0, right? What is b? Where do I get b? Just multiply. This is yi can be either plus 1 or minus 1. We have already seen yi, we have labeled as plus 1 or minus 1. Just multiply this entire equation by yi. You get yi is equal to, what will be the yi? Yi into yi is always positive. Plus 1 into plus 1 is positive, plus 1. Minus 1 into minus 1 is also minus 1. Is equal to plus 1. So yi is equal to yi square. Yi square is always plus 1. W transpose x plus b. So yi is equal to, for any point where alpha I is non-zero, yi is equal to W transpose x plus b. So b can be written as yi minus W transpose x for points with alpha I greater than 0. So for any non-zero point, for any point with alpha I non-zero, you can actually compute b by the equation yi minus W transpose x. So you get b over here. This is your hyperplane now. You define the hyperplane, and only those points with alpha I non-zero will participate in this hyperplane. And you should also note one thing. So this hyperplane, right? So your training points are xi, yi's, and x is your test point. W transpose x plus b, your x dash or whatever. Right? The way the training points participate in this context will be like, see, alpha I yi into xi. Non-zero alpha I points from the training point, from the training set. All those points with non-zero alpha I will define W. Alright. And when you define W, when you take a dot product of such points, so all those points with non-zero alpha i's will participate here. Right? Will contribute here into yi into, for those points, a dot product of the test point, right, xi dot x. So you will have, if you look at it, your decision surface, your decision hyperplane is W transpose x plus b is nothing but a summation over all training points, or the product of all training points, where alpha is non-zero into its corresponding yi into its dot product, those training points for which alpha is non-zero, dot the test point, right, plus b, whatever, right? B is essentially computed from the boundary points, primary points belonging to the canonical hyperplane. So you can see that what is happening in the case of a decision making in the context of support recognition is essentially you solve the SVM problem using the Lagrangian multipliers. That's what you can see, like the dual equivalent. You get some points with alpha is non-zero, and their labels will be used, and the dot product of those points with the test point will be taken, and that will become essentially like your decision function, right? So use a dot product of the training points with non-zero alphas, right, with the test point, and that is how you compute the decision, right? This is what it is for the case of alpha is equal to non-zero case. I just want to say that alpha is non-zero are essentially the points which will participate in defining the hyperplane. Let's look at the case of alpha is 0. There will be certain points where alpha is 0, all right? If alpha is 0, you can see that if alpha is 0, you don't have any restriction here. 1 minus ya into W transpose x plus b is less than or equal to 0. Sorry, is greater than or equal to 0. 1 minus ya into W transpose x plus b is less than or equal to 0. Which means that ya into W transpose x plus b is greater than or equal to 0. Which means that when alpha is equal to 0, from the complementary slackness conditions, this should be 0. Alpha is 0, so there is no restriction over here. 1 minus ya into W transpose x plus b is less than or equal to 0, which means that ya into W transpose x plus b is greater than or equal to 0, which is essentially like ya into W transpose x plus b is greater than or equal to 0. This is a correct classification matrix. So all those points where from the training point where alpha is equal to 0, you get this condition ya into W transpose x plus b is greater than or equal to 0. Those will be points where the classification is proper, points which are on correct side of the hyperplane. All right, let's go back and look at the slides again. All right, I just wanted to give you this context. How do you get to the math out there? How do you? The math is not well represented in most of the materials there, so I thought I'll just show you how this derivation happens. All right, so the minimization problem, the primal problem, is this. We wrote the Lagrangian equivalent of it, and once you have the Lagrangian equivalent, you can apply Karish conditions. The KKT conditions we have derived this W is this. The Lagrangian. From the Lagrangian we made of the observations. From the KKT conditions we can observe that points with alpha is equal to 0 fall either on the canonical hyperplane or on the correct side of the hyperplane, because we have seen that ya into W transpose x plus b is greater than or equal to 1. So either they can be on the boundary hyperplanes or they can be like off the boundary hyperplanes. So they are on the correct side. And the examples with ya is into W transpose x plus b is equal to 1 is basically like are non-zero alpha values, which means that alpha value is non-zero. Yeah, from the observations you can see that alpha is equal to non-zero, which means that ya into W transpose x plus b 1 minus ya into W transpose x plus b has to be equal to 0, which means that ya into W transpose x plus b is equal to 1, which essentially will be the points which are on the canonical hyperplanes, and these are points with alpha and non-zero, which means that they are the ones who define the canonical hyperplanes, essentially define the boundary hyperplanes, which essentially says that W is defined in terms of alpha I is defined as summation over alpha I yi xi, which means that only when alpha is non-zero, those points will contribute back to the decision surface or F. So which means that alpha and non-zero are the points which essentially define the hyperplane, which is the decision surface, which are essentially points which are falling on the canonical hyperplane. So those are points are called support definitions, and I've already shown you how you compute the B. All right. So the maximal marginal hyperplane I've already shown you. W transpose x plus b can be written as alpha I yi into xi dot x plus b, and the decision rule will become the decider point as belonging to plus 1 if W transpose x plus b is greater than 0, as belonging to minus 1 class if it's less than 0. And the most interesting observation you need to make over here is W. You know that W is summation over whatever alpha xi yi is the definition of W. You can see that from the equation. This is your hyperplane being learned. All right, for any given point, this is how you compute. And when you compute, only when alpha is non-zero, those points in the training data will participate. That's one observation. The second observation is you essentially take the dot product of the training points that participate with the test point to find the maximal marginal hyperplane. Essentially, like the maximal marginal hyperplane employs only an inner product computation between the data vectors. The hyperplane that you have identified essentially uses a dot product computation between the training points here and the test point. So your problem of computation, your essential computation that is involved in terms of the data, the actual excise is nothing but a dot product computation. This is a very interesting observation. The maximal marginal hyperplane employs only an inner product computation between the data vectors. The only way in which the data points participate in defining the maximal marginal hyperplane is with this dot product computation of the incoming point and the training points for which the alpha is unknown zero, right? And we actually move from here, and this is where the SVM algorithm becomes interesting, right? I'll just move on, and I'll give you a little more complicated context, which is essentially the same thing, where we are saying let us move and allow points to fall off the boundary, which means that these are the boundary points, and points can fall off the boundary, meaning the green one can cross this border, and the maroon ones can also, the brown ones can also, the squares can come here. Training patterns are not linearly separable. I'm complicating the stuff, but involve some noisy patterns in both classes. They lie interdispersed near the boundary to make the problem non-linearly separable. So we had a very nicely behaved context earlier. We are saying, hey, this is not nicely behaved anymore. Let us complicate it. Right? How do I handle this case? One feasible approach is let us minimize the errors. Right? That's the easiest thing that we can do. And how do I represent the problem then? We'll say, okay, the primary problem is defined as, in the case of the context with noisy points, I'll say I'll minimize again norm W square, but I'll introduce a cost and zeta is error. So instead of yi into W transpose, the functional margin y into W transpose x plus b greater than or equal to 1, I'll say, okay, it can actually go off the boundary, which means that see, zeta is the error that you make, right? So from the hyperplane, from the separating hyperplane, the error, this particular error is represented as zeta I. So in the optimization problem, we will with respect to a cost C, I mean basically like using a cost C, the cost of making a mistake, we'll try to minimize the what we call the cost of errors, meaning we'll penalize the points that make errors. So for every point belonging to the training set, there can be a zeta I, and the zeta I can be 0 or more, is positive, zeta I can be 0 or more. That's how we incorporate the noise, and there is a cost to it. A very high value for C, which essentially means that I don't want to allow anybody, because mine is the problem that I have in hand is a minimization problem. And if I have a very low value for C, what will happen is I'll say like I don't care too much about the points making mistakes. So and the zeta i's are essentially like the variables that represent the error introduced by jumping off the boundary. The noise is these are essentially these are in the optimization context, these are called slack variables. And this term C into zeta I is called a penalizing term. So this is a term that penalizes the errors. Right? The user given parameter C controls how much error we can tolerate. The problem will be represented like this. So all I do is I can allow even though like this was my original condition, I can allow points to do a little error, and that error is zeta I, and 1 minus zeta I. So basically like the functional margin will be greater than or equal to 1 minus zeta I. Right? That's what the context, and zeta I has to be greater than or equal to 0. So there can be points without errors, but there will be points with positive values of zeta I. Right, and we penalize those points which make mistakes. So we modify the problem like this, and correspondingly we'll also write a different Wolfe dual. So for example, just go back to our original problem, SVM problem. So correspond with this. So how do I get to this problem? How do I get this? Is basically like I've got this problem. I've written its Lagrangian right? I've got this problem, and I've actually like written the Lagrangian, apply the Karish-Kundakar conditions, and I do represent. I've told you, I've not mentioned you. There's a Wolfe dual equivalent. This is what the classic SVM case. Instead of solving this problem, we try to solve this problem and get basically represent, instead of the primary parameters W and B, I solve the problem in terms of the real parameters, alpha i's, which are essentially the Lagrange multipliers. And how do I get this problem? You can, I'm keeping this as an exercise for you. How do I get this problem? I just what do you call? I've got the equations for W here. All right, alpha I yi xi summation over here. So I can represent. So I substitute what is norm W square is W dot W, right? W dot W. So W dot W is essentially what is W dot W? All right. So I just substitute for W over here. What do I get? Ij alpha I yi xi. I can just substitute. What do you call? I can just substitute for this particular context, right? My problem reduces to what do you call the Wolferial problem, where I can write down the problem in a Lagrangian form, and my problem is reduces to what do you call reduces to the Lagrangian equivalent. I'll just keep you notes. I've given you this. The optimal condition. So basically, like you write the Lagrangian function, and from the Lagrangian function, you can write the dual equivalent of the problem. Right? It can be written as the Wolferial equivalent, which is essentially like the Lagrangian duality being applied there, and you just substitute back with the parameters that you have in place, and you get essentially like you get a problem defined in terms of the Lagrangian, and with respect to the conditions satisfied. The conditions are the Lagrangian duality. You essentially represent a maximization problem. You said like maximum L, so it will be like the problem equivalent duality. The real form will be maximize L with respect to the conditions, the KKT conditions. That's what it is. And when you want to represent L, what you know, like what is L? L is given here. Right? Your heart marginal here. You know L, right? Can you just substitute for W over here, and you get a problem. You get right half of non W W W. So your problem will the Wolferial equivalent will be maximize L with respect to the KKT. KKT is all these conditions to be satisfied. So you will, when you substitute back here W, you do the algebra. You will get what do you call? So W transpose half will remain alpha I yi xi, right? I comma. So there will be W dot. So there will be two summations I comma j, summation over I comma j, alpha j yi yj xi dot xj. That's the first term of, right? Then you need to what do you call? There's one more term over here. Then this term, right? In this term, you can see that when you substitute from the KKT, summation I is equal to 1 to m, summation over alpha I, right? That's one term, right? That's one term. Have here. Then alpha I minus alpha I summation, that summation will be minus alpha I yi into this term, right? This term will be like whatever be the context. So you can substitute for so alpha I yi. You know that summation over. So this will be alpha I into yi into. So the algebra will be alpha I into yi into this summation. The summation W, you know that W alpha I yi xi dot x plus b you can plus b. So what will be the sum here? You get an alpha I yi term over here. From the alpha I yi term, what you get is this will cancel, right? Alpha I summation over alpha I yi is equal to 0, which means that the summation will cancel. So you get the second part of the thing will go off as a 0. So what you get is L will be summation over alpha yi xi dot xj, alpha j yi yj xi dot xj right? That'll remain, and then this that alpha I part will remain. And if you substitute it back, what you're going to get is this form. All right. So you get a what do you call the L will be and that'll be a what do you call the form of the problem, right? With respect to the conditions alpha I y summation alpha I y is essentially like the conditions that are specified over here. Alpha I y is equal to 0 and alpha I greater than 0 for all I. These are essentially the part of the KKI. Alpha I y is equal to 0 and less than or equal to 0. So this will be the form. So essentially, like your minimization problem will become what do you call? You have when you multiply, you can see that this is the minimization problem. The equivalent duality form will be maximal L. So will be written as max L subject to the KKT conditions. Max L you will once you substitute it back here. Let me show you once again. Once you substitute back here to this equation, L can be basically the values over here can be substituted over here. Basically, W you substitute back, you erase this, you substitute the value for B is essentially like for those points with where the X alpha is non-zero. So once you substitute, you will see that there is a half over here, and there is a one of, you will get a similar term here, and what do you call this half minus that one will take over. So you get a term like maximum L summation over maximum L LB maximize summation I is equal to 1 to M alpha I minus summation alpha I xi whatever that alpha j yi yj xi xj, and that's what you'll get. And that will be maximization problem. You can write that as a minimization problem like this. Here's the context. The problem it will become a minimization problem. It's a maximization problem, so it's maximize x is equal to minimize minus x. So you can see that what do you call your L will become like this. All right. So the Wolfe dual, this is something that I've missed to mention you. So how do you get from this problem to the equivalent Wolfe dual? You initially write the Lagrangian equivalent of this, and then apply the KKT conditions, which are essentially the necessary and sufficient condition for the convex quadratic problem. And you substitute it back to the original, the Wolfe dual equivalent. Wolfe dual is defined as the max. So equivalent of this primal problem, the Wolfe dual is max cell subject to the KKT, right? Max cell subject to the KKT. And the maximization problem will have, when you substitute it back from the KKT, you will be able to remove all those. Essentially what you do is you are substituting for the primal parameters with respect to the dual parameter, which is essentially the Lagrangian multipliers, and you get an equation in terms of, you get an optimization problem defined in terms of Lagrangian multipliers. All right, that's how you get to the Wolfe dual equivalent of the linear hard margin SVM. So what you do here is, and the problem Wolfe dual equivalent is max cell with respect to the Lagrangian, such that the Lagrangian conditions are satisfied. That's the Wolfe dual definition. Maximize with respect to alpha, maximize L with respect to alpha, such that the Lagrangian, the KKT conditions are satisfied. And when you, so you have an equation for L in front of you, you substitute it back in L, you get a maximization problem, and then from the algebra you can see that you can write that as a minimization problem because max cell is equal to min L. So I want to give you this as an assignment because that's the reason why I have not derived the rest of the things. Again, one more page of paper I could have written that. So what I want you to do is remove all the primal parameters from here and represent the Wolfe dual, and the Wolfe dual would be this. When you substitute back and when you write the Lagrangian, the Lagrangian dual, which is Wolfe dual, as max over alpha L, such that the KKT conditions are satisfied. It's essentially alpha I, the things that you basically like kind of you don't ignore primarily the primality the optimality conditions, and that's what it is. That's how you get the Wolfram dual. So how you derive the Wolfram dual, and those who are not very interested in all the math out there, we can very well ignore it, but that is how you get it. All right. So let's go back to our original context. We'll take a break later, just after this, because it's the same thing. So we allow points to follow the boundary. The noisy case follows the boundary. We write the primal problem with a condition for penalizing the points that make errors. And penalizations are essentially like you introduce slack variables. Slack variables are essentially the errors that you make. I mean, slack variables essentially represent the errors that you make, the errors that certain points make when they fall off the boundary, and they are represented as slack variables of optimization problem. You penalize them with the penalization parameter. And equivalently, what you do there is, once you have the primal problem, you go through the same set of steps. That's why I've given you this particular thing. You write again Lagrangian, soft margin SVM. You write the Lagrangian, you apply KKT, dou L by dou W, dou L by dou B. Now you have one more parameter called zeta, dou L by dou zeta is equal to 0. You get these kind of equations. Right? You get complementary slackness conditions, alpha I into this thing is equal to 0. Now you have one more primarily like kind of one more variable called zeta I, which represents the slack variable. So beta I is a corresponding Lagrangian multiplier. So beta I zeta will be equal to 0 for all I. So this is what it is. And alpha I, the Lagrange alpha and beta I has to be greater than or equal to 0. That's basically the Lagrange multipliers are positive. All right. Once you have this, what you do is you apply, basically you make observations. Very similar to that. You can have three cases here. Alpha is equal to 0. Alpha is equal to 0 from, let me see whether I can open both the. So look at here, alpha is equal to 0. Alpha is equal to 0. It's the simplest case, alpha is equal to 0, which means that if this has to be 0. So alpha is equal to 0, this will be non-zero. Alpha is equal to 0, you can see like from the dou L by dou zeta I conditions, you will see that dou L by dou z is essentially like you get c minus alpha I minus beta I is equal to 0. That's what you get. And in alpha is equal to 0, alpha is equal to 0, c is equal to beta I. You can see that alpha is equal to 0, c is equal to beta I. C is equal to beta I, meaning c is a positive thing, it's a cost, beta is positive. If beta is positive, which means that zeta I has to be 0. Right? Beta is positive, zeta I has to be 0. So alpha is equal to 0 meaning c is equal to beta I, which means that zeta I has to be 0. Zeta I has to be 0, which means that if zeta I has to be 0, so you get alpha is, you know that alpha is equal to 0, 1 minus, so this is 0, 1 minus yi minus double transpose x plus b is less than or equal to 1. That means y into double transpose x plus b is greater than or equal to 1. Which means that these are points which are on the correct side of the plane. So yi into double transpose x plus b is greater than or equal to 1 for certain points, and those are the points which are on the correct side of the head plane. Right? That's basically the correct points. There can be another case where alpha is between c and 0. So alpha is between c and 0. Then what will happen is like alpha is between c and 0. C minus alpha I between c and 0, which means that beta is between c and 0, which means that this number will be positive. C minus a number which is less than c, which means this is positive. Beta will be positive. Beta is positive, meaning zeta will be 0. Zeta will be 0. So, but now we know that alpha is between c and 0. Alpha is non-zero. C is positive. Alpha is non-zero. Alpha is non-zero, meaning this has to be 0. This particular term has to be 0. Right? This has to be 0. And we know that since this is positive, beta is positive, that means zeta is 0. So 1 is equal to yi into w transpose x plus b is equal to 1. So these are the points which falls on the bottom, the canonical hyperplane. So those points for which the solution, the training points for which the solution says alpha I, the corresponding alpha is between 0 and c, those will be the canonical hyperplane. Those will positively contribute because w is again, you can see that only non-zero alpha I will contribute, right? Points with non-zero alpha I will contribute, right? And when alpha is equal to 0, which means that beta I is 0, beta I is 0, meaning zeta I can be greater than or equal to 1. So if alpha is equal to 0, beta I is equal to 0, which means that zeta is greater than or equal to 0, which means that yi is the y and double transpose x plus b. So alpha is 0, this alpha is positive, which means that this has to be basically like the what do you call alpha is positive. This means that yi minus zeta I minus y into double transpose x plus b is equal to 0, which means that double transpose x plus b is greater than or equal to 1 minus zeta I. So essentially, these are the points that make errors or mistakes. Right? These are the observations from this particular context. Nothing more than what we have seen in the earlier case. The algebra is a little different. But we have a little more, and again, the dual equivalent, the Wolffe dual would be max L with respect to max L with respect to the KKT conditions, and you get Wolffe dual equivalent like this. You can just from the derivations you can substitute for the primary variables. You get your problem defined in terms of the dual variables. Right, that's what it is, and we can make KKT. This is what I've shown. The Lagrange multiplier greater than 0, and difference the observations you can make. Right. All I want to say is, so we have seen a SVM on very similar terms where you allow points to fall off the boundary, but again we have not seen a proper nonlinear context. Right. Let us take a break, and in the meantime, I don't want you to what do you call it? We can take a break for 15 minutes and then come back around 11:45. I'll give you insights in the nonlinear subproduct condition, which is interesting. The takeaway from whatever we have seen here is an SVM is a problem where the problem is a problem of, I mean, we start with a linear separable case, which is very straightforward, hard margin SVM, where we said the problem of finding the maximal margin hyperplane is what SVM attempts, and that can be solved by pausing it as an optimization problem, as a QP problem, and we allowed points fall off the boundary in the soft margin SVM. We said again it's a QP problem, and the QP problem, rather than solving the primary problem, we can solve it by finding the equivalent Lagrangian dual, and it's a convex quadratic problem. So the necessary and sufficient condition is KKT. We apply KKT conditions. We derive the Wolffe dual and write the Wolffe dual form, and we solve that Wolffe the dual equivalent form to get. For every point in the training set, we get alpha I values. On the alpha I values of a point, we can see whether the point is actually on the boundary, off the boundary, or is actually defining the boundary. Right? And then, yeah, that's pretty much about it. And one more interesting observation that you need to make is when you actually define the hyperplane, which is W transpose X plus P in terms of the points in the training set where alpha is non-zero, you will see that the only way in which these training points participate in the context is as dot product computations, essentially like the only computation that is involved with the data points in defining the maximal margin hyperplane in the case of a hard margin SVM or a soft margin SVM is in the form of a dot product computation. Right? I stop this particular session over here, and we'll come back and we'll look at non-linear SVMs. Right? I'm stopping the recording.